morning, everyone. Before writing software, our next speaker was a chemical engineer working for a landfill consulting company where he helped design landfills and gas cleanup systems. But today, he's here to talk with you about the Factorio software architecture. So let's please welcome John Konecny.
Well, hello, everyone. So welcome to my talk. Today we're going to be talking about, as you could tell, the Factorio software architecture. But before I get into that, I want to put a little disclaimer for my company. This is my own work, my own opinions, so hopefully nothing's too embarrassing for them in here, which I don't think will be the case. But that said, I do like the work I do, and it's pretty rewarding. And the thing I do work on is called OncoKB, which is a cancer research website. Basically, it relates mutations in tumor cells in a cancer tumor cell to potential treatment options. So if you or someone you care about is going through cancer and doesn't like the options they have presented to them, it's definitely worth looking at. Just have to keep in mind that it's intended for doctors to look at. So if you don't understand it yourself, you can always have a doctor take a look at it and see if they can use that. The other thing I want to do is acknowledge some people who helped me out with this talk. So some people from the rock programming language community, spelled ROC, very nice community, by the way. Highly recommend contributing to them if you're looking for an open source project. So Sam, Anthony, Anton, Brendan, Fabio, very much appreciate your help on this. My friend and former colleague, Tom, appreciate that help as well. And last but not least, my wife, very supportive. So let's get into it. So I've been fortunate enough to work on a lot of greenfield projects in my career, which means I've been unfortunate enough to experience the pain of a lot of design decisions that were pretty bad. And one of them, I remember very, I guess fondly, maybe is a good word for it, is one where it was a system where it was an internal company website where basically there was no latency. We had everyone on-prem. The server was on-prem, probably about 5 concurrent users. Database size probably measured in gigabytes. If I'm exaggerating, probably more realistically megabytes. So very, very, very small system. However, even though this is a small system, the page load times were measured in seconds. So pretty bad. Yeah, not good. And I remember distinctly the users being upset with this, obviously. They wanted to go back to Excel, and it's probably like one of the worst insults you could give a developer is to say, I'm going back to Excel. And yeah, but something I remember distinctly was one of my managers. He was like, we use the latest technology. Like, this shouldn't happen. We use the latest version of .NET. We use the latest version of React or Angular. I can't remember exactly what we were using at the time. But he said it like it didn't matter about the other decisions we made. That somehow if we used a blazingly fast framework, we're good. No other worries. And really, it's like what I was doing was really dumb. I was doing things like, fetching extra data from the database that was unnecessary because it was easy for my ORM. I was copying data, and the way I did that was by serializing it as JSON and deserializing it immediately. So rather than just doing an assignment operator because I thought it was easy. And so it's no wonder that the performance was god-awful on this. And I think really the problem is that we don't focus on what's important about software. And I think what is the most important thing about any piece of software is that you get the data to the users as efficiently as possible. If you fail to do this, your software sucks. Like, no one wants to use it. I failed to do this. Sure, I got the data to my users, but I got it in seconds. And that's pretty unacceptable, especially given the constraints of my problem. It doesn't even matter, really, if you're a software engineer, or a software architect, or a UX person. Like, this is the problem you always have to solve. And so the question then for me becomes, well, why? Why do we get to this point? How do we always screw this up? Or maybe not always, but how did I screw this up? And I think what we're missing is something that all engineering disciplines have, but we don't have yet, and that's math. Now, I know people don't like math as much, but The thing about math is it gives an engineer the ability to simulate a decision, to simulate a decision of whether or not it's viable to go forward with. So for me, sure, I didn't have a lot of experience, but had I had mathematics in my side, I could have said, maybe this whole serializing JSON thing, maybe that was a bad way to clone a piece of data. Maybe I should just go with a regular assignment operator. But the math would have told me that's a dumb idea, and I wouldn't have had the experience of falling on my face to teach me that lesson. So with all that in mind, I was playing this game when I was thinking about this kind of stuff. And this game, for those of you who don't know, hence the title of the talk, is Factorio. And Factorio is a game where you crash on a planet, and you have to harvest resources and build a factory, obviously. And there's something weird about this game. Not so much that the game itself isn't not fun. It's definitely an awesome game. You should check it out. But it feels like programming. Now, clearly, you're not writing lines of code. You're just building a factory. But it really feels like programming. Like that same part of your brain that's thinking about design and all that kind of stuff when you're coding, it comes up. And you run into similar problems that you run into with regular programming. You run into scalability problems. You run into situations where you have conveyor belts all over the place, and so it's spaghetti. You have no idea what's going on anymore. And sometimes you do such a terrible job, like I have many of time, that you have to rebuild the entire factory from scratch, a full rewrite. And so thinking about this, why does it feel like programming? Well, fundamentally, this is a video game, so it is a piece of software. And because it's a piece of software, that means everything is represented by ones and zeros. So we have pieces of material flowing through our factory. Those are just structs. Those are just classes. And these structs and classes are flowing through machines. And these machines, since they're software, are just functions acting on our data. So we have data and we have functions. And we build a giant factory with it. So really, Factorio is in fact a low-code, no-code solution. Now, maybe it's not Turing complete, and maybe it doesn't solve all your problems, which pretty much means it's a low-code, no-code solution. But it's still what you're doing. It's still fundamental to what we do as software engineers. And so if Factorio is a lot like building a factory, and software engineering is a lot like Factorio, does that mean building a factory itself, a physical factory, is like building a physical factory is just like software engineering? And if that is the case, can we learn from that? What can we gain from that? And so an engineering discipline devoted to this, devoted to building factories and scaling them, is chemical engineering. So question is, how did chemical engineers become engineers? Because maybe we could just steal their ideas. There's no need to reinvent the wheel. Let's just go for it. So let's take a look. How did they become engineers? Well, you have to keep in mind that there's been chemical manufacturing for thousands of years, all the way back to ancient Mesopotamia. You had people making beer and all that good stuff at relatively small scale. But it wasn't until around the late 1800s that the modern concept of chemical engineering came to be. Now, it's worth noting that the situation, the environment that people were in when they were making, or when this was coming up, when people started becoming chemical engineers. And so there were three major powers that were a big part of chemical manufacturing. The first major power was Great Britain. So Great Britain, the way they kind of trained their engineers was not really using engineers. They would basically have people work their way up to the top in their companies, and they eventually would be given the opportunity to start designing chemical plants. Now, the issue with this is that people were very siloed. They had to learn through their own companies, essentially, about all the ways that they were making mistakes, and they couldn't learn from other groups. I mean, not that it was illegal or anything, but it's just the same problem that we have with siloing they had. The next major power was Germany. So at Germany, they were kind of in a golden age of chemistry. And so they had a lot of great chemists, And so they had an ability to manufacture very sophisticated chemicals. But the problem is that you needed good chemists to understand the chemistry. And so they weren't good at the engineering, which means they weren't really good at the scale part. So they generally produced more sophisticated chemicals at lower volumes. The last major power was the United States. Now, the United States generally wanted higher volume. And so they generally hired mechanical engineers, taught them a little bit of chemistry, and then they would produce less sophisticated chemicals at higher volumes. So in this environment, we have a man by the name of George E. Davis, nice beard, and he is a chemical manufacturing consultant. So like probably many consultants in the world of software engineering, he has seen a lot of terrible decisions made, and he's very upset. And he thinks that there's a better way to do this. Now, this man is from Great Britain, and he really hates the siloing, as I mentioned earlier. He really believes that there should be a fundamental principle, what he describes as not mechanical engineering, chemical engineering. And he's arguably the first chemical engineer. And so he is so passionate and so strong-willed that he starts to lecture about these ideas, about what the essence of chemical engineering should be. How do we train the next generation on this? And apparently his lectures were so good that eventually he wrote a book. And this book is called A Handbook of Chemical Engineering. Now, this book has a lot of things that are just eerily similar to the same problems we face as software engineers, but don't want to rattle all of them off, so I'm going to be a little more targeted. So the first thing he mentions that's pretty relevant to our talk today is that you shouldn't be wasting resources. So he talks about how sometimes he'll go to a chemical plant and he'll see people venting boiled water, steam, into the atmosphere. Now, in terms of energy costs, relative to other things to boil off, water is very expensive. So you really, really don't want to do that. Generally, in modern chemical engineering, you would recycle the steam. So really, this is kind of the same problem we face in software engineering, where people just make decisions ad hoc, in ad hoc ways, and they end up with giant AWS bills. And it's only through trial and error that people have figured out, oh, well, maybe I shouldn't do all this crazy Lambda stuff on AWS. Maybe I should just go with a traditional server. The other thing is to not trust vendors. So he mentions how people come up to him and say, I have this great invention, George. You're going to love it. It's got the best performance, blazingly fast performance probably, and you should use my stuff. And George says, that is great. However, you should test that. You should absolutely test to make sure that is actually the case. And on top of that, better still, maybe use something like a production-like environment, because in his words, it's pretty expensive to change things in production. You'd much rather do that in a lower environment, catch it early, and then pivot. The next thing, and probably the biggest idea he has, is really the fundamental idea that there are commonalities across different industries and that we really shouldn't be siloing ourselves. Now, really, he's thinking in terms of testing equipment, right? Like, this is kind of like a fundamental understanding that we use common pieces of equipment. We should be able to understand and reason about them effectively and test them well. And really, this is kind of the same problem we face as software engineers. We face the problem where there are different industries like gaming, web development, embedded systems, these kinds of things where we kind of view each other differently. We kind of view it, yeah, sure, it's programming, but we don't view the problems faced as very similar. And I believe that's a mistake. I think we can learn a lot from each other, and I think that there's probably fundamental principles that govern exactly what makes good software in each industry. So unfortunately for Davis, his ideas didn't really take off the way he had hoped in Great Britain. And there's a lot of arguments as to why this is the case, but most probably it was because they didn't have a good pipeline from universities. Part of his plan was that people would be trained essentially in universities, and so because they were kind of doing a lot of apprenticeships, so to speak, for their chemical manufacturing plants, it didn't really work. However, in the United States, it did take off, and they were already training engineers, and so they really liked the idea of, oh, well, what if we just train people a little bit better in chemistry? Maybe they'll be ready to go. The only problem here is that There was an accreditation process. So universities were kind of guessing and hoping that they were teaching the next generation well, but it wasn't really well organized. But that worked okay until something happened in 1914. Archduke Franz Ferdinand gets assassinated, which now means the United States is starting to manufacture a lot to support the war effort. But even more so once in 1917 they enter the war. So now there's a greater demand for more sophisticated chemicals to be produced at greater volumes. And on top of that, another competitor, Germany's gone, as far as because we're fighting them. So there's no need to compete with them anymore. So anyway, in this environment, now there's a new wave of thinking, and we need to be more refined, more exact about what it means to be a chemical engineer. And so in this environment, we have another man by the name of Arthur D. Little, not as good of a beard. And he comes up with this idea of unit operations. Now, unit operations are definitely basically the same idea as George E. Davis, but probably a better marketing strategy that he had, and that eventually became the norm. Anyway, so what a unit operation is it's a unit of work on chemicals. So you could think of something like a reactor, where it's like I have chemicals and I do a reaction. And similar to something like different algorithms we have in software engineering, you have different kinds of equipment that are effective. Things that you would pick that always work, but maybe can be slower in some certain circumstances, or different kinds of equipment where they would only work in very niche scenarios. This is kind of the essence of a unit operation. So anyway, he proposes this idea to MIT. And MIT says this is a great idea. Let's go with it. And so that becomes the way. That becomes the standard. And then because people wanted to be a part of this, that's when an accreditation process starts to happen in the United States. So universities all start to get behind this idea of unit operations. Now, it's worth noting that unit operations aren't very scientific. They're not based on first principles of chemical engineering. It's really black box testing. You're just looking at a piece of equipment and you're saying, this is the performance. You don't fully understand all the reasons why. Maybe you have some intuition, sure, but it's kind of not great because you still require testing. What's something that's very nice about modern engineering is you don't need the testing necessarily. You have an ability to just kind of work out some equations and see whether or not you're going down the wrong path generally. So in the 1950s, we start to have the rise of nuclear power and a big boom in the pharmaceutical industry. So now the chemicals are starting to get even more sophisticated. It's more critical to make better decisions earlier on in the process, not just at the pilot plant, the production-like environment scale. And so there's this rise, this new wave of thinking called transport phenomenon, which is the way chemical engineers are currently taught. And really, it's the scientific principles of engineering that is taught here. And it's a way of basically not having to build everything out to have an idea of whether or not it's viable. So the question is, for us, if this is the path we could take, and it worked for the chemical engineers, and we want to do that same path, where are we now? And I would argue we're in probably George E. Davis's day, where we have a lot of grumpy people saying that we need to get our stuff together, and we need to figure out a better way to do software engineering. But clearly, the way chemical engineers seem to grow quite quickly was this idea of unit operations. So next question then becomes is, do we have unit operations? Because if we have unit operations, maybe we can kind of catapult ourselves into the next wave of software engineering. And for me, obviously, I think the answer is yes. And I believe these are unit operations. And keep these in mind. I believe these unit operations, or I should say, unit operations act on data, right? So we're not chemical engineers, but so we don't act on chemicals. So for us, we act on data. So all of these revolve around data. So let's go through each one of them. So the first one is a map. So a map, sure, it could be what you might be thinking already of like an array map. But what I mean by map here is just any piece of data. Arbitrary piece of data, I am converting from one data to another piece of data. So in Factorio, you could see this in action by converting from some copper ore into a copper plate. So there you go, simple as that. In code, we could do something with JavaScript, where I'm just converting between an object and a number. Now here I'm just counting the number keys because in JavaScript, basically objects act like hash maps. So here I'm just counting the number of keys, but you could see just one piece of data to another piece of data. The next one is a filter, so it removes data that you're not interested in. So in Factorio, you can see this in action by me just removing some coal here, dumping it in that box over there, and I just leave my iron ore. In code, I could do something very boring, like remove a bunch of odd numbers out of my list. So there you go. Next one is sort, and I believe some of you probably know what a sort is. So yeah, sort a list of numbers, or any piece of data. Now I couldn't think of a good analogy to Factorio, so I went with question mark, because I thought that would be kind of funny. So there you go. And I'm not interviewing anytime soon, so I didn't feel like doing quick sort. So there you go. Dot sort it is. Next one is validate. So validate is you check to see if the data meets your expectations. If it does not, you return an error. If it does meet your expectations, you pass it through. So in Factorio, we can see this in action where we have my furnace here, and it doesn't have enough fuel. So it's a little sad, and it can't work. So it's in an invalid state. So in code, I could do something like validate an email. And how I'm doing that is by just checking to see if there's an @ symbol. So clearly a terrible algorithm for checking to see how valid an email is. But there you go. Next one is I/O. So this would be file reads and writes, network calls, all that kind of good stuff. So in Factorio, we can see this in action with our mines, or just harvesting resources generally. So here I'm getting some copper ore. And in code, I didn't feel like doing anything complicated, so I'm just going to print to the console, hello world, classic. Next one is a distribution. So a distribution is you're making the decision about whether or not where to direct your data. So you try to figure out which function to call. So in Factorio, we can kind of see this in action by the splitter here, and it's going to split our copper and our copper ore and our coal into two separate streams. And a good example of this would be your classic HTTP server. So here I check to see which endpoint a client is trying to go to, and then I make a function call based on that. And then there's obviously the default behavior of if I can't figure out which page you want to go to, I give you a 404. Next one is authentication and authorization. So for those of you who don't remember the difference, authentication is identify who the user is. Authorization is once I know who you are, I determine whether or not you are able to go to that resource. So in Factorio, we have biters who try to destroy your base. So you got to make sure you're well prepared for that scenario. Next, so with my example here, we're logging in a user, and we're checking to see if Valentina here has the ability to launch a spaceship. Now, this is a reference to Kerbal Space Program, which is a very good game, by the way. I would highly recommend it if you're into any kind of spaceship kind of simulator. However, the second one is not as good, so probably not worth your time. But there is Kitten Space Agency coming up. It's in development, so if you like the first game, probably worth looking at. Next one is global state read and write. So this is just reading and writing from memory globally. Here in Factorio, I just have a box, and I'm just dumping all my copper ore into it. For our coding example, I'll go with the classic Fibonacci memoization solution with recursion, of course, because we're in LambdaConf. So here we go. I'm sure you guys have already seen this before, but here we have the cache that's going to be our global state. Last one is a panic. So if I'm in an invalid state, I crash the program. Factorio, that would be blowing up some nuclear reactors. So we gotta, there you go. And in code, that would look like something like an unhandled exception. Okay, so we've gone through a bunch of unit operations, and they're all well and good. But obviously, it's one thing to say these are what our operations are, but it's another to kind of see these in action and how this actually could help us. So let's do that. Let's take a look at that. So what we're going to do is we're going to take a look at making a decision between doing client-side rendering or server-side rendering in a web development scenario. So I'm going to make this website, or I made this website, and this website just shows a bunch of patients, and that's about it. And yes, those drugs, for those who are paying attention, are fallout drugs. So they take fallout drugs. So how are we going to use unit operations? What are the steps? So the first step is we're going to determine the unit operations that are involved. The next step is we're going to measure the performance of each unit operation. Once we do that, we can sum up the results and have an estimated performance for the whole end-to-end application. Finally, we can kind of do some looping here, some iteration here. So we can kind of see, okay, where can we improve? Maybe there's a better algorithm we can use or a better general approach. Maybe we don't want to do a certain series of unit operations. Maybe we just get rid of them entirely. So let's do the first step. So the first step is determine those unit operations. So for our server-side rendering case, we are going to first try to get the index.html page, which will cause our server to start fetching patients from the database. So this is on the server side. We're going to map the data from the database into HTML. The client will then start downloading the HTML from that server. It will then start to download the CSS from that server. And then finally, the client can render the page. So those are the operations. For the client-side version, we're going to obviously start off with the same thing where we're getting the HTML page. Then the client will start to download the HTML. It has to download CSS and JavaScript. And then finally, once it has that JavaScript, it can finally start getting that data. And so it's going to make a request to an endpoint called get a request to the endpoint API/patient. Then we finally have the server who is able to start doing things, and it's going to download, or it's going to get data from the database as well, map that data into JSON this time. Then the client can download the JSON, then they can parse the JSON, then map it to HTML, and then finally render. A lot more steps. So now that we know the unit operations involved, we now need to figure out what the performance is going to be for each one of them. So here I have a scenario, or well, here I'm just looking at getting data from the database. I'm not going to go through each one of these because I feel like it'd be a little repetitive and not so much fun. So we're just going to focus on just this one. Here on the x-axis, you see that I have total number of patients, and on the y-axis, I have the runtime. Now, granted, I probably should have measured the total number of patients in terms of bytes and the total runtime in terms of clock cycles, but man, it was so much easier to do this way, so I'm going to do it this way. But you can see it's pretty unsurprising that we have, O of n operation proportional to the patients being loaded in. But it is also nice to do these kinds of things because let's say you're not really good with databases and you don't really know how to do proper querying. Well, if you started seeing a polynomial function here, you would say, wait a minute, that doesn't make any sense. And so this is kind of something in action showing you something in action where maybe you could catch things early where you're like, wait, that's not going to scale well. That doesn't make any sense why I'm getting that performance issue. So the next one is then to sum up the results. So we do all of the rest of those unit operations and all that good stuff, and now we're going to see the results. So here I have a comparison between what actually happened versus what I predicted, and we could see about a 25 millisecond error. So the diamond is the predicted, and the triangle is the actual result. So for under 200 patients, it's pretty good for server-side rendering. And just to keep in mind, this is also a local host, so there's no latency to worry about, or, well, pretty much no latency to worry about. And for our client side, as expected, it's slower. So it's about 100 milliseconds for under 200 patients. And for whatever reason, I got less of an error. I am not enough an expert in performance to understand entirely all the reasons why, but as you can see, we get pretty decent results. Okay, so now we can start performing some what-if analysis. Now we can see under what scenarios will this particular solution work and where will it not work so well, or these two options. So what I did, because again, it was easy, was I looked at latency. Like, what if I had real latency on this system? What would that look like? But you could also imagine scenarios where you might say, well, what if I try a different algorithm? What if I try a different approach altogether? Maybe I could find a hybrid approach. Maybe I could find a way of doing both server-side rendering and client-side rendering to get the best of both worlds. So anyway, looking at the latency increase, I made an assumption of relatively slow internet. So I have 100 millisecond latency, and I have a download speed of 200 megabits per second. So pretty slow. And unsurprisingly, you can see that the server-side stuff is doing pretty well. See that under 200 patients, we get under 500 milliseconds of response time, which isn't, it's not the best. It's not the best performance, but it's good enough where you're probably not going to make your users very angry. But the client side is way too slow. I would say over a second is pretty bad, and you probably don't want to go that route. So maybe your conclusion here would be, okay, clearly client side is stupid, never do it, always go server side. But to me, that's not really an engineer's way of thinking. Under these constraints, sure, it doesn't work as well. But what if we have different constraints? What if we have a different scenario? Now, here I kind of cheated because I didn't feel like doing a whole nother setup or anything like that. So what I did was, well, let's see what happens if I downloaded a lot more patients. So let's say I tried to download 50,000 patients to my page. You can see now server-side rendering starts to fail. Now the reason why it's so much slower is because the way I designed it, the HTML is growing faster per patient than the JSON. So eventually there's a cutoff point where the JSON file relative to the HTML file is significantly smaller. That said, it's still 30 seconds. 30 seconds for loading a page. I don't think a lot of users would be very happy. So it's still a bad idea, but maybe here in this scenario, let's say hypothetically you really needed those 50,000 patients. You might say, well, maybe we shouldn't do JSON. Maybe we should try to do something else, maybe some sort of binary format to speed up the whole process. But again, because we did this engineering approach, we are aware that we have to make these kinds of decisions. So what does the future hold? Well, I think the future for us is with a new kind of transport phenomenon, and obviously it's not going to be chemistry focused, it's going to be data. So I believe that there will be eventually data transport phenomenon, and I'm hoping to get other people on board with this, including people watching and the people in this room, to believe in this, and then hopefully we can give our children the benefit of actually good software and performance software. If you're interested in more of this kind of stuff, I highly recommend Casey Muratori's Performance-Aware Programming. He goes over how to do testing of performance, and I needed a lot of his help, so I very much appreciate that course. The other one is Domain Modeling Made Functional by Scott Voloshin. I'm sure plenty of you know this guy. He is very much into the functional world. He's an F# developer. But anyway, I believe his book is really good at teaching you about how to think about gluing unit operations together, because my theory is that an imperative style is pretty good for putting together the internals of a unit operation, but outside of a unit operation, the declarative style is a much better approach. So definitely worth a look. And the last one is it's a playlist entitled Terry Reynolds, which is on the MIT Chemical Engineering channel. And it's a playlist where Terry Reynolds talks about all the history of chemical engineering. So if you find that interesting, which I suspect is a small amount of people, you could go check that out. So with all that in mind, I encourage you to go out there and play some Factorio, and always remember to do what the math tells you. Any questions?
Thank you very much, Don. Do we have any questions from the audience? Yes.
Yeah, really great analogy. I like that a lot. Do you think my feeling with formal methods and software in general is that maybe we just don't have the incentives that chemical engineering has in terms of the expense and real-world impact of getting things wrong? It's so easy to put together software, you can do it on your laptop, that maybe we just will never be forced to shape up.
Yeah.
If that makes sense?
Yeah, no, that makes sense. Yeah, so basically what you're getting at is we can just write software really quickly. Why waste all this time on proving whether or not this is going to be a good idea? Well, my counter to that is we have legacy software. There's old infrastructure written in COBOL. If it was truly that easy to rewrite, then we wouldn't have that problem at all. That said, it probably wouldn't be necessary to do this for every little thing you do, but I think for bigger projects that you know you're going to be working with for years, you have to think about these things. If you just say, I'm going to just do some random React project and then hope for the best, you're asking for a terrible result.
Thank you. Any other questions?
Somewhat of a joke question then, everyone. How do you think space age affects this equation?
Yeah, well, I'm really bad at the game, so for me, it's beyond my comprehension. I wish I could give you a better answer. Maybe we could fill in the question mark, though. That might be, I don't know how we can sort that out.
Fair enough. My real question is, a more appropriate, on-topic question, I suppose, is do you think, how does this type of math approach and that apply to like big design up front or versus agile? And like, it seems like it leads towards more of a design up front kind of thing to try and analyze and make sure you understand as much as you can before you do something, whereas the trend in the industry seems to be more, go quick iterations as fast as we can.
Yeah. No, I think that makes sense. Yeah, so I think the design up front stuff is, obviously has a bad name to it. But I like like what some software architects like to talk about, where software architecture, their definition is the parts that are hard to change. So I don't envision, I hope, the takeaway doesn't become, well, I need to tell my developers every line of code they need to write. What I hope ends up happening is that people say, okay, this is the general flow of the code. I trust my developers as grown-ups to figure out the implementation details. Because in my experience, the overall data flows are generally more challenging to fix if you've massively screwed them up. Obviously, if you haven't massively screwed it up, you can fix it. So that's my hope. Does that answer your question?
Yeah, I think so.
All right. Anyone else? Yes.
You said your HTML was growing faster than your JSON.
Yeah.
Do you mean like, just like there was more text generated?
Yes.
Okay. I didn't know if it was like scaling differently.
Oh, yeah.
Yeah, okay.
Yep, that was it.
Coming to you.
Hi. I've worked on performance topics for like the last 3 years, and I've also played Satisfactory, not Factorio, but I feel like when I was playing the game, I've had the same revelations of, hey, this just feels like programming, and I'm just refactoring my code every time as new requirements come in. So I get that kind of approach, and I feel like I like the talk. I felt one part where we could have maybe gone deeper with the Factorio Satisfactory, where it applies to real, is on the scaling part, where I feel like you were mentioning before of like, this is kind of a, how does it work with Agile? But I feel like first you'll build it, but you'll have to kind of rethink it at some point, and that's how software development goes anyway. And I feel like the biggest part that I had parallels were like, okay, now the math part of like, I need to do 100 copper bars to get the 20 cylinders, and I need 5,000 copper ore, and how do I scale that? And that's kind of like, okay, now I need to write a function and like do the unit operation timing there and scale and like run 20 containers or 50 containers to do this. And this is just more of a thought and their parallels I had rather than a question, but yeah, so I like to talk, yeah.
I see what you're saying. Yeah, I agree. I did want to go deeper into it, but it turns out that I talked way faster during this than I did any of my practice runs, so I didn't think I'd have time.
Yes, be right there. And we have plenty of time for questions, like another 10 minutes.
I like this idea of what if programmers are following the same path as chemical engineering. Do you think it would be possible to learn from the path that chemical engineering took and skip some of the steps? Like, is it necessary to go through this unit operations, or could we jump to the transport phenomena and first principles?
That's a good question. So in my mind, it's the easiest step to take. So it's something that doesn't require you to be a good theoretical mathematician or an expert in performance testing. You could do the unit operation testing yourself today. So that's why I proposed that. But yeah, I mean, obviously if someone wants to just skip the line and fix everything right away, I mean, sure, yeah.
Anyone else? All right, well, let's have another round of applause for John Konecny.